Welcome back everyone. In this lecture, we will actually see the characterizations of completely reducible modules. So, let us recall the definition and the statement. Okay. So, what we mean by completely reducible G modules? A module V is said to be completely reducible. A module V, so it is a G module said to be completely reducible if for any given submodule, let us say capital W, which is proper inside V, we have another submodule W dash inside V such that V is indeed equal to W direct sum W dash. One can also talk up to isomorphism, but anyway, because we have assumed they are all submodules, so we just demand V is equal to the direct sum of these two submodules. So, this is the definition of completely reducible. So, we have the following theorem. Okay, as I promised, I will prove only one characterization. So, let us start with the G module V. So, let us say G is given Lie algebra and V is finite dimensional G module. Okay. So, one can assume everything is finite dimensional, not a problem. Okay. So, then V is completely reducible if and only if V is a direct sum of G submodules, irreducible G submodules. Okay. So, one way actually obvious, one can prove using the induction on the dimension of V. So, other way we need to do little bit work. So, first of all, to use the induction, so we need to actually see that any submodule of a completely reducible module must be completely reducible. So, that is actually a side proportion. So, let us make this here. So, here is another statement. Okay. So, if we start with completely reducible module, okay, if G module V is completely reducible, and W is just a submodule, G submodule, then we have W is also completely reducible. So, let us say call it CR. Okay. If V is completely reducible, any submodule of V must be completely reducible. So, what is the proof? The proof is very simple. So, we start with some submodule of W and then see how to get the complement of that inside W. Okay. So, we have to use the fact that it can have complement inside capital V. So, let X being a submodule. So, this is a proper G submodule. Okay. So, now you can see that submodules being transitive, X is also proper submodule inside V. So, this is proper submodule inside V. So, now V being completely reducible, so that implies that you have some X dash inside V, which is G submodule, such that V can be written as X direct sum X dash as G modules. Okay. So, this is there already because V is completely reducible. Now, we are looking for complement of x inside W. So, what will be the natural thing to do? So, we can actually look at W intersection x dash, which is going to be G submodule, and we will see whether it is complement or not. Okay. So, the claim is this is indeed complement. The claim is W is exactly x direct sum W intersection x dash. So, to prove this, what we need to check? We need to check two things: x plus W intersection x dash should be W, that is the first thing. The second thing is x intersection W intersection x dash should be trivial. So, note that trivial means 0 space. So, x intersection W intersection x dash is subspace of x intersection x dash, which is trivial because x and x dash are complement to each other. So, this implies that V equal to x plus x dash and x intersection x dash is trivial. So, that implies that 2 is true. Okay. So, 2 is fine. So, we need to check that W is indeed sum of x plus W intersection x dash. Let us start with W in W, which is a element of V. So, W can be written as some x plus x dash. Now, x is coming from capital X, x dash is coming from capital X dash. Note that x is being a subspace of W, that implies x dash, which is W minus x, is also element of W. That implies that x dash is inside W intersection x dash. So, that implies that W is in x plus x intersection x dash intersection W. So, this is what we wanted to prove. Okay. So, that completes the proof. So, whenever we have some complement x dash inside V, using that one can actually get the complement of x inside W into W. So, this proves that any completely reducible module if you take, then submodule of that will be completely reducible. So, now we will go back to the theorem, the proof of the theorem. So, proof of the theorem. So, one way is obvious. Okay. Suppose assume that V is completely reducible. Suppose V is completely reducible. So, then we need to prove that V is a direct sum of irreducible modules. Okay. To begin with, if V itself is irreducible, then there is nothing to prove. Okay. If V is irreducible, then there is nothing to prove. So, we take V is not irreducible. Okay. So, that means it will have a proper submodule. If V is not irreducible, that means it is reducible. So, then there exists proper submodule, proper G submodule inside your V. So, now by proportion, earlier proportion, we can see that W is irreducible. Using the proportion, we can see that W is completely reducible. So, now V is being completely reducible. So, V is completely reducible implies that V can be written as W direct sum W dash for some W dash which is a proper submodule G submodule. Again by proportion we can see that W dash is also completely reducible. So, now note that dimension of W and dimension of W dash both are smaller than dimension of V, because both of them being proper submodules. So, that implies that by induction W and W dash both of them are direct sum of irreducible submodules. Okay, because they are direct sum of irreducible submodules. So, that implies V being double sum W dash is a direct sum of irreducible submodules. Okay. So, this completes one side of the proof. By induction, one can see that V is itself direct sum of irreducible submodules. Now, for the converse part, we can assume that V is direct sum of irreducible G submodules, then we need to prove that V is completely reducible. So, for that we need to start with some proper non-zero submodule and then see that it has complement. Okay. If it is 0 module, then there is nothing to prove. So, we need to start with the non-zero submodule. So, conversely, assume that V is a direct sum of irreducible G submodules. So, then what we will do? So, we look at that direct sum and then pick one of the irreducible submodule that is there in that direct sum. Let us say that is V1. So, V1 is irreducible G submodule occurs inside that direct sum, occurs in the direct sum. Okay. So, we are fixing the direct sum and then simply taking one irreducible G module there, and then we can collect rest of them and then we can make another direct sum. So, V2 will be sum of indeed the direct sum of the rest of the irreducible submodules. Occur in that direct sum. Okay. So, basically we are grouping. So, we take V and then it is just a direct sum of some irreducible submodules. So, then we pick one here and then we call it V1. So, this is one irreducible component and then we collect the rest here. So, this is direct sum of the rest. Okay. So, since direct sum of G submodule is G submodule, V2 will become G submodule, V1 is also G submodule. So, now let us start with some W, okay, which is proper inside capital V, and we can assume it is non-zero, otherwise there is nothing to prove. So, now W being proper inside V, we want to find, okay, what is our goal? So, our goal to find complement of W, to find complement of W inside capital V. Okay. So, that means we need to find W dash such that V is equal to W direct sum W dash. So, how one can do that? We just simply use this information about V1 and V2 and then find the complement. So, now there are two possibilities. One possibility is W intersection V1 can be 0. Okay. There are two cases. Let us see the cases. Case 1, just to look at W intersection V1. So, this could be 0 or it could be full. Okay, when you take W intersection V1, which is submodule, which is G submodule of V1. So, that implies W intersection V1 is either 0 or entire V1. So, we consider the first case when it is 0. So, when it is 0, then you can easily see that this W becomes actually submodule inside V2. Okay. So, this implies W becomes submodule inside V2. So, now by induction V2 is a direct sum of, so this is a direct sum of irreducible, So, that means by induction V2 is completely reducible. Okay. So, since W is inside V2, okay, so if W is equal to V2, then there is nothing to prove, but otherwise W will have actually complement. Okay. Because if W equal to V2, then it already has complement V1. So, if W is proper, then it will have actually complement. So, let us take that complement, let us call it W dash. This is by induction. So, you have another G module W dash such that V2 is equal to W direct sum W dash. So, now it is easy to see that V is nothing but W1 direct sum W direct sum W dash. So, now you can see that W has this complement V equal to W V1 direct sum W dash. Okay. So, this tells you that W has complement inside V. Now, what is the case 2? The case 2 says W intersection V1 could be V1. Okay. So, that is the case 2. So, in that case we have to see that what happens. So, now look at V2 intersection W1 W, which is a module in V2. Okay. So, this cannot be equal to V2. So, this has to be proper. If it is equal to V2, then W becomes equal to V. So, this is since proper, so it must have a complement. So, by again by induction, okay, this is completely reducible module by induction, because it is a direct sum of irreducible module. So, we can say that it has a complement. So, V2 can be written as V2 intersection W direct sum W dash. Okay. So, now it is easy to prove V is actually exactly equal to W direct sum W dash. Okay. So, this is something I will leave it to check. This is simple check. Okay. So, once you have this condition, W intersection V1 is V1 and W dash is the complement of V2 intersection W, then this W dash must be the complement of W inside V. So, that means complement of W exists inside V, and because W dash is G submodule of V2, that will imply that W dash is G submodule of V. Okay, that tells you that any submodule actually has complement. So, indeed what we have proved, completely reducible G modules are equivalent to a direct sum of irreducible modules. Okay. So, we already seen a fact about finite dimensional G representations. So, if we take any finite dimensional representation, we proved that that can be written as direct sum of indecomposable representations. So, let us recall, and this is true for any finite dimensional representation and finite dimensional Lie algebra. So, if I take G to be a Lie algebra, V is finite dimensional, that implies V is a direct sum of indecomposable modules. Indecomposable G module, G submodules. Okay. So, this is easy to prove by induction on dimension of V. And another thing that we have seen, irreducible implies indecomposable. Okay. So, that is what we have seen, and now we have proved that completely reducible is same as a direct sum of irreducibles. Okay. So, that means we have kind of some inclusions. Okay. So, we have this completely reducible modules, reducible G modules, and then which is contained in, of course, the finite dimensional modules. Okay. And we are also seeing that the irreducible modules so that is contained in indecomposable G modules. Okay. This is all there as general facts. So, now if you want to understand, for example, completely reducible module, then it says that first you need to understand all irreducible modules. Okay. And if you are interested in understanding all finite dimensional modules, then you should understand all indecomposable modules. Okay. So, that is what this general observations tells. Of course, when G is something not semi-simple, like for example, solvable Lie algebra and so on, then it is easy to construct non-completely reducible modules for G. Okay. So, now if you bring in Wile's theorem, which says that for any semi-simple Lie algebra, we have completely reducibility for all finite dimensional representation. So, that says that this containment is indeed equality for finite dimensional representation, for semi-simple Lie algebras and finite dimensional representations. So, if G is semi-simple, then this completely reducible modules, let us call it CR, is same as finite dimensional representation. Okay. So, because of this Wile's theorem, so one can actually reduce our study of finite dimensional representation to completely reducible modules. In particularly, to understand them, we need to understand first all irreducible modules. Okay. So, this actually motivates us to actually study all possible irreducible finite dimensional representations of semi-simple Lie algebras. So, in this course we will see that how to classify them for GLN and SLN. Okay. So, more or less the ideas are all same. So, the highest weight representation theory, which is developed by D.N. Verma, actually gives all irreducible modules for finite dimensional irreducible modules for semi-simple Lie algebras. So, that entire theory, whatever you see for GLN and SLN, can be easily generalized to semi-simple Lie algebras. So, because I have not done the structure theory of semi-simple Lie algebras in this course, so that is why I am assuming only GLN, which we have seen the structure. So, we will just work out the details for GLN. Okay. So, this is actually kind of again tells some of the important problems that we encounter in representation theory. Okay. So, first problem is classify all finite dimensional irreducible G modules. Okay. The second thing is, once you are done with this, then we have to propose an algorithm. Okay. Find a natural efficient algorithm to decompose any completely reducible module to irreducible submodules. So, even though we know that any finite dimensional representation of semi-simple Lie algebra is completely reducible using Weil's theorem. So, it is not that easy to actually decompose that into irreducible representation. So, we have to actually come up with some efficient algorithm. So, we will see that how one can do that for SL2, and then later I will try to actually work out some example for SL3 and then demonstrate already like in SL3 itself it becomes much more complicated. Okay. So, this is the goal of this course. So, as I said, like this complete reducibility also can be actually weakened further. So, any sum of irreducible submodules also will become direct sum of irreducible submodules, and then that will imply that that module is completely reducible. Okay. So, what we will do actually we will start with the representation theory of SL2 before moving into actually general theory of SLN and GLN. So, we need to actually understand completely what happens in SL2. So, let me just recall the definition of SL2 again, and then probably I will give examples of SL2 representation. So, then later we will actually move to the general theory of representations of SL2. So, recall that SL2 of C. So, this is nothing but the traceless matrices. So, which is spanned by X, H and Y, where X is the upper triangular matrix 0, 1, 0, 0, and H is the diagonal matrix 1, minus 1 on the diagonal. Y is the lower triangular matrix 0, 0, 1, 0. Now, we have this commutator table, the bracket xy is h and the bracket hx is 2x and the bracket hy is minus 2y. Okay. So, here are some examples of representations of SL2C. So, recall that if you are interested in constructing a finite dimensional representation of SL2 of C, so what we need to do is, let us say V is given to be the vector space. So, we want representation, so SL2 action on V. So, then you need this map from SL2 of C to this GL of V. So, given by x goes to xv, y goes to yv and then h goes to hv. Okay, this is the let us say map V. So, once you give the images of the basis elements, you can extend this linearly and then get this linear map from SL2 to GL of V. So, now to make this phi into SL2 action, okay. So, SL2 action obtained by satisfying this following commutator relation. Okay. This becomes SL2 action if whenever we take xv yv, so that means xv yv minus yv xv, that should be equal to hv. Similarly, we have other things, hv xv should be 2 xv and then hv yv should be equal to minus 2 yv. So, if these operators satisfies these three relations, then that will immediately give you SL2 action on this capital V. So, this is one way to actually get abstractly the SL2 action. Okay. For that purpose, we need to verify that these things are true, but in most of the time we will be considering very natural representations. So, for which we do not need to really verify these things. So, it will become automatic. For example, SL2 acts on C2, okay, via this matrix multiplication. So, that is clearly SL2 module. Okay, this is 2-dimensional SL2 module, and it is easy to see that this is indeed irreducible module. So, this is irreducible module. Okay, I will leave it as exercise. And similarly, SL2 acts on this SL2 itself via adjoint representation, via adjoint map. So, this is also irreducible representation. Okay. So, this is also irreducible representation. So, similarly, one can get SL2 acts on the one dimensional space. Okay. SL2 acts on C trivially. Okay. And this is the only action you can get it on the one dimensional space, because any element of SL2 can be written as commutator of. So, any basis element can be written as commutator. So, that means the action of H, when you take the commutator, then it should be 0. Similarly, the action of x and y should be 0 on this one dimensional space. Okay. So, this gives you one dimensional representation, which is also irreducible representation. So, we have naturally these representations, okay, and I will actually tell you in the next class how to construct all irreducible representation in a more uniform way. So, we will first see some concrete example. For example, SL2 naturally acts on this homogeneous polynomials of degree m. So, that action actually gives you irreducible representation, and then we will see abstractly how to construct irreducible representation. So, using that we will actually make some one-to-one correspondence between irreducible representations of SL2 and a set of non-negative integers. Okay, I will stop here. So, we will continue with the SL2 representation theory in the next class. Thank you.